Now, we have a few more indeterminate forms that can sometimes lead into L'Hopital's rule problems. And some of these indeterminate forms are 1 to the infinity, 0 to the 0, and infinity to the 0. And you might be wondering, well, what do functions look like where this occurs? And so we'd be looking at something like the limit as x approaches a of f of x to the g of x. And we're going to use a little trick here. And that trick is we're going to use the fact that the exponential e and the natural log, these two functions, they undo each other, right? So I'm going to do this over here. I'm going to say e to the natural log, and then this is of f of x to the g of x. So this is equivalent. And then the next thing I'm going to do is I'm going to apply a log property. And so that log property is I'm going to bring the g of x in front of the natural log. So we have e to the g of x times the natural log of f of x. And then there's one more thing that we're going to do, and that is we are going to bring that limit into the exponential. And this is really going to rely on continuity here. We need nice functions. And so if we do have these nice functions, we're going to have e to the limit as x approaches a of g of x times the natural log of f of x. And the last thing I want to do is make it clear why this is helpful. Okay, so the reason that this is helpful is those forms that we had up above, 1 to the infinity, 0 to the 0, and infinity to the 0, those now in this form are going to look like 0 times infinity usually, which is a form that we can typically use L'Hopital's rule for. What we're going to write here is if the limit is of the form in 1 to the infinity, 0 to the 0, and infinity, I'm going to say or here, or infinity to the 0, use the fact that the limit as x approaches a of f of x to the g of x is equal to e to the limit as x approaches a of g of x times the natural log of f of x. Okay. And this is exactly what we're going to do in our next example. We are on to our last example here using L'Hopital's rule. And let's first figure out what form this limit's in. Okay. If we were to let x go to infinity, okay, then this 3 over x would go to 0. So the stuff that's in the parentheses is just going to approach 1, while the exponent up here is going to continue to grow without bound. So the form of this limit is 1 to the infinity. Okay. And the thing that makes this an indeterminate form here is normally when we raise 1 to a power, it gives us 1, right? But also, if this number is something bigger than 1 and you raise it to a large power, you expect to get a really large number. Okay? And the issue is that while each one of these individual limits is 1 and infinite, it really depends here on, are we approaching 1 quicker than we're going off to infinity, or vice versa? Or is there or maybe they approaching things at a similar rate? Okay, we don't know. And so this is really indeterminate. We don't know what 1 to the infinity here is going to result in. Okay? And it won't always result in the same thing. Okay? So let's see here. To get started, we want to rewrite this as e to the limit as x approaches infinity. Our exponent will come down because we're going to take the natural log. So we have x natural log 1 minus 3 over x. And one thing that I like to do from here is, rather than continuing to write e over and over again, let's just do a little bit of side work here down below. Okay. So we're going to start just looking at this limit as x approaches infinity of x natural log of 1 minus 3 over x. Okay. And let's think about what form this limit's of. Okay. Well, the x here is going to go to infinity, but this natural log of 1 minus 3 over x, well, the 3 over x will go to 0, so this is going to approach the natural log of 1. The natural log of 1 is 0. So it's of this form. This is an indeterminate form that we've actually seen before. Okay, and we're going to use actually the exact same trick that we used the last time. Okay, so what I like to do is this one that's going to infinity, I like to rewrite it as 1 over that function. And I should be even more specific, dividing by 1 over that function. So we're going to divide this by 1 over x. And the whole point is, right, is if we were to go and simplify what we have here, we'd end up back with what we started with. Okay. So these two things, they are equivalent, but we are now in a form where we can use L'Hopital's rule, because this natural log part here, this is still going to be going to 0. And this 1 over x, though, now is going to also be approaching 0. So this is of a form that we can use L'Hopital's rule on. So let's start differentiating here. I'm going to continue to write that LH, just letting you all know we're going to apply L'Hopital's rule. So this derivative up top might be a little messy here at first. We're going to have 1 over 1 minus 3 over x. But don't forget, we need to take the derivative of this inside function, which is 1 minus 3x to the minus 1. So if we were to take the derivative of this, we should get positive 3x to the minus 2. So times 3x to the minus 2. All right, so there's that. And then we want to take the derivative of the 1 over x. And again, remember, 1 over x is just x to the minus 1. So if you were to take the derivative, we should get minus x to the minus 2. Now, the next thing we could do is we could just note here that these x to the minus 2's are going to cancel. Or you could do a little bit more simplification. It's really up to you. I would say, let me make sure I have my limit sign in here. I'm going to add that back in. But I would say to make this problem a little bit easier, we'll just start off by canceling those x to the minus 2's. But yeah, I need my limit sign in here. So L'Hopital's rule, limit as x approaches infinity. And so then this becomes the limit as x approaches infinity of 1 over 1 minus 3 over x. I still have this 3 here. It's just the x minus 2 is going to cancel. So maybe I'll just put that 3 in the numerator of this fraction. And then this is all over. And again, the x minus 2's we're going to cancel. So all I'm left with is minus 1. And so I'm going to rewrite this one more time before I actually try to take the limit. So this can now be rewritten as, right, if you just divide by minus 1, then we could rewrite this as minus 3 all over 1 minus 3 over x. And you can now see that this 3 over x is going to go to 0, so all we're going to be left with is minus 3 over 1, or how about minus 3? Now, a lot of people, when they do these problems, because this part took so much work, it feels like this is our answer, minus 3. But remember, our answer is actually e to the minus 3. So if we go back up here, that limit that was in the exponent, again, was minus 3. So we get e to the minus 3. This is our answer right here. But maybe, yeah, I'm just going to leave it like that. This is our answer here.